What is weather? Imagine stepping outside in the morning. A breeze carries the scent of rain, clouds drift across the sky, the sun peeks through, and maybe there's a chill in the air. That moment is weather, the ever-changing conditions of the atmosphere around you right now. Weather is short-term. It can change by the minute, hour, or day. It includes temperature, humidity, wind, air pressure, and precipitation. By contrast, climate is the big picture, the average of weather patterns over decades or centuries. Deserts, rainforests, and polar ice caps each have their own climate, predictable patterns that shape ecosystems and life itself. We track the weather every day, but climate is what we measure to understand our planet's long-term heartbeat. Earth's atmosphere, our invisible shield. All weather happens within Earth's atmosphere, a delicate blanket of gases hugging our planet. It's about 78% nitrogen, 21% oxygen, and small amounts of water vapor, carbon dioxide, and other gases. Though it feels infinite, the atmosphere is shockingly thin compared to Earth's size, like an eggshell or an apple's skin. It keeps us warm, shields us from meteors, blocks harmful UV rays with the ozone layer, and holds in the air we breathe. Without this protective shield, our world would swing wildly between scorching days and freezing nights, and liquid water could not exist. All life depends on this thin veil. It is the stage on which weather's story unfolds. Air pressure, the hidden push. Invisible yet powerful, air pressure is the weight of Earth's atmosphere pressing down on everything. At sea level, this pressure is about 14.7 pounds per square inch. As you climb a mountain, air pressure drops because there is less air above you. Changes in air pressure drive the weather machine. High-pressure systems push air outward and downward, creating clear skies. Low-pressure systems draw air inward and upward, forming clouds and storms. When pressure drops quickly, winds pick up. When pressure rises, skies clear. This constant push and pull keeps air in motion, and keeps weather in motion too. Temperature, the dance of heat. At its heart, weather is a story of energy moving around the globe. Temperature is the measure of how fast air molecules jiggle and move. When sunlight strikes Earth, it warms the surface, which then warms the air above it. Heat moves in three ways. 1. Conduction, direct contact. Think of your feet warming on hot sand. 2. Convection, rising warm air and sinking cool air. This creates winds and clouds. 3. Radiation, energy traveling through space, sunlight. This endless dance, from equator to poles, land to ocean, day to night, fuels weather's constant changes. Humidity, the air's hidden water. Even the driest desert air contains water vapor. Warm air can hold more moisture than cold air. That's why summer days feel muggy. We measure this as relative humidity, the percentage of moisture the air is holding compared to what it could hold at that temperature. When warm, moist air rises and cools, its moisture condenses into droplets, forming clouds, fog, or rain. Humidity affects how hot or cold we feel, how storms grow, and whether plants thrive or wilt. The water cycle, nature's endless loop. All weather connects to the water cycle, a timeless loop that never stops. The sun heats oceans, lakes, and rivers, causing water to evaporate into vapor. This vapor rises, cools, and condenses into clouds. Eventually, droplets become heavy enough to fall as rain, snow, or hail. Some water runs off into rivers, some seeps into the ground to become groundwater, and much flows back to the sea, ready to start the cycle again. This invisible dance connects every raindrop to oceans thousands of miles away. The sun, weather's master engine. The ultimate driver of all weather is the sun's solar energy warms Earth unevenly. Equator hotter than poles, land heats faster than ocean. This imbalance sets air and water in motion. Warm air rises, cool air rushes in to replace it, that's wind. Ocean currents carry heat across the globe. Storms swirl where warm and cold air collide. all of it powered by sunlight streaming from 93 million miles away. Air masses, moving weather. Air masses are huge pockets of air that form over oceans or continents. They take on the temperature and humidity of where they sit, dry and cold over Siberia, warm and wet over the tropics. When different air masses meet, weather changes fast. Cold fronts can spark storms. Warm fronts bring gentle rain. These invisible giants drift with winds, bringing heat waves, blizzards, or monsoons. Winds, Earth's restless breath. Wind is air in motion, caused by differences in air pressure. The bigger the difference, the stronger the wind. Local breezes form when the sun heats land faster than water. Sea breezes during the day, land breezes at night. Global winds blow in predictable belts, trade winds near the equator, westerlies in temperate zones. High above, jet streams steer storms around the world. Wind carries seeds, shapes deserts, and powers storms. It is Earth's restless breath. Humans and weather, watching the sky. Since ancient times, people have studied the sky. Farmers needed to know when to plant. Sailors watched the clouds to navigate oceans. Folklore filled with sayings. Red sky at night, sailors' delight. Today, satellites orbit Earth, supercomputers run models, and meteorologists analyze mountains of data. But even now, weather keeps its surprises, reminding us that we live in a thin, swirling world where the next breeze could bring rain, sun, or snow. The atmosphere's layers. Troposphere, Earth's weather factory. Close your eyes and imagine the air that surrounds you, stretching up as far as a commercial jet can fly. This is the troposphere. The shallow, restless layer where almost every drop of rain, every gust of wind, and every snowstorm is born. The troposphere reaches about 8 kilometers, 5 miles, at the poles and up to 18 kilometers, 11 miles, at the equator, thicker where it's warm because warm air expands. Temperatures drop the higher you go. That's why mountain peaks stay icy. This layer contains about 75% of all the air in the atmosphere and nearly all the water vapor. It's a churning sea of moving air, convection currents constantly rising and sinking, stirring the clouds and storms. Stratosphere, home of the ozone layer. Above the troposphere floats a calmer sea, the stratosphere. Here, air moves in broad, stable layers, perfect for the ozone layer, our shield from the sun's ultraviolet rays. The stratosphere stretches from the top of the troposphere up to about 50 kilometers, 30 miles. Unlike the troposphere, temperatures rise with altitude here, because ozone absorbs UV light, heating the air. This temperature inversion keeps the stratosphere layered and stable. It rarely mixes with the troposphere. The ozone layer sits around 15 to 35 kilometers up. Without it, life on Earth would be bombarded with harmful UV radiation. Commercial jets often cruise at the lower stratosphere to avoid turbulence and storms below. Mesosphere, the fiery shield. High above, the mesosphere is Earth's coldest layer, yet it protects us from constant cosmic bombardment. Here, meteors meet their fiery end, streaking the night sky as shooting stars. The mesosphere stretches from about 50 kilometers to 85 kilometers, 30 to 53 miles. Temperatures can plunge to minus 90 degrees Celsius, minus 130 degrees Fahrenheit, the coldest part of Earth's atmosphere. It's too high for planes and balloons, too low for satellites, one of the least explored layers. Millions of meteors enter this region daily. Friction with the thin air vaporizes them into trails of light. Thermosphere, the dancing lights. Above the mesosphere, the thermosphere shimmers with the glow of auroras, cosmic fireworks ignited by the sun's charged particles. From 85 kilometers to about 600 kilometers, 53 to 375 miles. Temperatures soar to 2000 degrees Celsius, 3600 degrees Fahrenheit. But it would feel cold, because the air is so thin. The International Space Station orbits here. The northern and southern lights, aurora borealis and aurora australis, appear when solar winds hit gas molecules in this layer, painting the sky green, purple, and red. Exosphere, the edge of space. The exosphere drifts outward, where our atmosphere fades into the vacuum of space. Here, hydrogen and helium atoms drift away like tiny escape artists. Starts around 600 kilometers, 375 miles, and stretches thousands of kilometers out. So thin it's almost space, some gas molecules can orbit Earth for a while before drifting off. Satellites like weather and communications satellites orbit here. How layers interact. Though each layer has its character, they're not sealed away. Energy and particles move between them in subtle ways that ripple through our weather. Strong thunderstorms can punch into the lower stratosphere, injecting water vapor that affects jet streams. Volcanic eruptions send ash and sulfur into the stratosphere, blocking sunlight and cooling Earth's surface for years. Solar flares and cosmic rays from space can energize the thermosphere, influencing communication signals and satellites. Weather balloons and satellites. To understand our skies, we launch explorers, weather balloons that drift skyward and satellites that circle high above, watching the entire swirling dance. Weather balloons carry instruments to measure temperature, pressure, and humidity through the troposphere and stratosphere. Data helps meteorologists predict storms days in advance. Satellites orbit in the exosphere, providing global images of clouds, ocean temperatures, and storm movements. Jet streams, rivers of wind. At the boundary between the troposphere and stratosphere, rivers of air race around the globe, the jet streams. These high-speed winds, reaching over 160 kilometers per hour, 100 miles per hour, steer weather systems. They form where warm and cold air masses meet. Most famous is the polar jet stream. Pilots use jet streams to save fuel and time flying west to east. Polar vortex, the frozen whirl. Near the poles, a swirling crown of icy winds, the polar vortex, keeps frigid air locked in place. But sometimes it wobbles, sending icy blasts far south. The polar vortex is strongest in winter, swirling around the Arctic and Antarctic. When it weakens or splits, cold air spills southward, causing extreme cold snaps in places like North America and Europe. The delicate balance. From Earth's surface to the edge of space, our atmosphere's layers weave an invisible fabric. Change one part, and the ripples reach far and wide. Climate change, ozone depletion, and air pollution can upset this balance. The layers work together to regulate temperature, block radiation, and support life. Understanding this balance helps us protect our fragile sky. Energy from the sun. Solar radiation, Earth's energy budget. Every gust of wind, every raindrop, every tide is powered by our star, the sun. Imagine 1.3 million Earths could fit inside it, yet its warmth is just right for life to thrive. The sun radiates energy across space as light and heat, solar radiation. About 30% of this energy is reflected back by clouds, ice, and Earth's surface. The rest is absorbed by the atmosphere, land, and oceans. This balance, what comes in versus what goes out, is Earth's energy budget. Small shifts can tip it. More greenhouse gases trap extra heat, melting ice, lowering reflection, and warming the planet more. Reflection and absorption, nature's mirrors. When sunlight hits snow, water, or forests, some of it bounces away like a mirror, some sinks in, warming the surface. Surfaces with high albedo reflect more sunlight. Fresh snow reflects up to 90%. Dark forests or oceans absorb more heat, which warms the air above. Clouds play both roles. They reflect sunlight by day but trap heat at night. How land is used, cities, deforestation, changes local reflection and absorption patterns. Albedo effect, ice, snow, and feedback loops. Earth's icy regions act like giant mirrors, the albedo effect. As they shrink, less sunlight bounces away, and the world warms faster still. The Arctic sea ice and glaciers help keep polar regions cool by reflecting sunlight. Melting ice exposes darker ocean or land, which absorbs more heat. This creates a feedback loop. More warming leads to more melting. Why equator is hot, poles are cold. Why does the equator bake under endless heat while the poles stay frozen? The answer lies in the angle of sunlight. Earth is round, so sunlight strikes the equator directly, concentrated and intense. At the poles, sunlight spreads across a larger area and must pass through more atmosphere, losing strength. The tilt of Earth's axis creates seasons, but the general heat pattern stays: tropics warm, poles cold. Heat redistribution, Earth's great circulators. Earth is always trying to balance extremes, moving heat from the blazing equator to the frozen poles. Warm air rises at the equator, cools, and sinks around 30 degrees latitude, creating the Hadley cells, powerful air circulation loops. These cells drive trade winds, desert belts, and tropical rainforests. Ocean currents, like the Gulf Stream, also move heat, warming Europe's climate. Coriolis effect, Earth's spin and weather's twist. If Earth didn't spin, winds would blow straight. But our planet's rotation twists them into graceful arcs. The Coriolis effect deflects moving air, to the right in the northern hemisphere, left in the southern hemisphere. This shapes trade winds, westerlies, and giant swirling storms like cyclones and hurricanes. It explains why hurricanes spin counterclockwise in the north and clockwise in the south. Day and night, temperature swings. Every sunrise brings warmth, every sunset a chill. But why does the ground cool so fast while the ocean holds its heat? Land heats and cools faster than water because it has lower heat capacity. Deserts can swing from scorching daytime highs to near freezing at night. Oceans moderate coastal climates, warmer winters, cooler summers. Urban areas trap heat, creating urban heat islands that stay warm even at night. Seasons, the tilt that changes everything. Earth leans at a gentle tilt of 23.5 degrees, enough to shape our seasons, from tropical monsoons to snowy winters. Without the tilt, we'd have no real seasons, equator always hot, poles always frozen. As Earth orbits the Sun, the hemisphere tilted toward the Sun experiences summer. Solstices mark the longest and shortest days. Equinoxes are when day and night are equal. Climate zones, drawn by the Sun. From equator to pole, our world divides into climate zones, each sculpted by how the Sun's energy lands. The tropics, near the equator, stay warm and wet, breeding rainforests. Subtropical zones become deserts like the Sahara, dry, descending air limits rainfall. Temperate zones, where warm and cool air collide, create fertile regions with 4 seasons. Polar zones remain icy, with short summers and long, dark winters. Human impact on Earth's heat balance. We shape the energy balance, too, burning fossil fuels, clearing forests, and blanketing the sky with greenhouse gases. Greenhouse gases trap heat that would otherwise escape into space. Cities change the local albedo with asphalt and concrete, trapping more heat. Aerosols from pollution can reflect sunlight and cool regions, but they also harm health. Understanding our impact is vital to keeping Earth's energy balance stable. The water cycle, Earth's endless river. What is the water cycle? Every drop of water you drink has likely passed through clouds, rivers, oceans, maybe even a glacier. On Earth, water never stays still. It flows in a timeless loop that connects us all. The water cycle, or hydrological cycle, is nature's recycling system. Powered by the sun, water evaporates, condenses, precipitates, and runs off or soaks into the ground. It ties together atmosphere, land, oceans, plants, and even deep underground aquifers. Without it, no rain, no rivers, no life. Evaporation, sunlight lifting water. Stand by the shore on a hot day. You can't see it, but billions of invisible water molecules drift into the air, lifted by the sun's warmth. About 90% of water vapor comes from oceans, seas, and lakes. Plants also release water through transpiration, adding moisture to the air. Heat energy breaks bonds between molecules, freeing them to rise. Warmer temperatures speed up evaporation, cooler temps slow it down. Transpiration, plants helping clouds grow. Every leaf is a tiny fountain. Through microscopic pores called stomata, plants breathe out water vapor, adding to the air's moisture. Forests and jungles are huge contributors to local and regional rainfall. Rainforests recycle up to 50% of their rain through transpiration. Cutting down forests can disrupt this cycle, making dry seasons longer and droughts worse. Condensation, turning vapor into clouds. As moist air rises, it cools. Invisible vapor clings to tiny dust particles, forming droplets. Billions of droplets make a cloud, a floating lake in the sky. The higher air rises, the colder it gets. Cold air holds less moisture. Droplets join together, growing larger. When they get too heavy, gravity pulls them down as rain, snow, sleet, or hail. Clouds, nature's floating reservoirs. A single puffy cumulus cloud can hold hundreds of tons of water. From gentle wisps to towering thunderheads, clouds are the sky's great storytellers. Types of clouds: cirrus, high wispy; cumulus, fluffy; fair weather, stratus; blanket-like, cumulonimbus, storm clouds. The shape and type tell meteorologists what weather to expect. Clouds move with winds, carrying rain far from where the water first evaporated. Precipitation, rain, snow, and everything between. When droplets combine and grow heavy, they tumble down as rain. In colder air, they freeze into snowflakes, each one a masterpiece of ice geometry. Precipitation is the atmosphere's way of returning water to Earth. Types include drizzle, rain, sleet, snow, freezing rain, and hail. Topography affects it. Mountains force moist air up, cooling it and squeezing out rain, creating rain shadows on the far side. Runoff, rivers shaping the land. Raindrops gather into rivulets, streams, and mighty rivers. They carve valleys, floodplains, and canyons, sculpting the face of the planet. Gravity pulls water downhill, feeding streams, lakes, and eventually oceans. Floods can nourish farmland but also cause destruction. Humans build dams and levees to manage runoff, but these alter natural flows. Infiltration, water's journey underground. Not all water races to the sea. Some seeps down through soil and rock, trickling into hidden underground reservoirs. Infiltration replenishes groundwater, our unseen, precious supply for drinking and farming. Porous soil and sand let water soak in easily, clay and concrete block it. Aquifers can store water for thousands of years. Groundwater, the hidden river beneath us. Beneath your feet may lie rivers and lakes you'll never see, vast aquifers that millions rely on every day. Groundwater feeds springs, wells, and even streams during dry seasons. Overdrawing groundwater can cause land to sink, subsidence. Pollution can contaminate it for decades, making protection crucial. The water cycle's balance. From ocean to cloud to rain to river to sea again, the water cycle binds us all in its quiet rhythm. Disruptions like deforestation, urbanization, and climate change can upset this balance. Warmer air holds more moisture, leading to heavier rainfall and stronger storms. Understanding this cycle helps us conserve water, manage floods, and protect this fragile balance for generations to come. Winds and air currents. What causes wind? Every breeze you feel is air on the move, driven by differences in temperature and pressure. Warm air rises, cool air sinks, and Earth's rotation gives it a twist. Sunlight heats Earth unevenly, equator versus poles, land versus ocean. Warm air is lighter, it rises, creating a low-pressure area below. Cooler, heavier air rushes in to replace it, that's wind. The bigger the difference in air pressure, the stronger the wind. Local breezes, sea and land winds. Stand by the coast on a summer day and you'll feel nature's daily cycle. The sea breeze by day, the land breeze by night. During the day, land heats faster than water. Warm air over land rises. Cooler ocean air flows in sea breeze. At night, land cools faster than water. Now the ocean is warmer. Warm air over water rises, and cooler land air blows out, land breeze. This pattern refreshes coastal regions daily. Mountain and valley winds. Even mountains breathe. Warm air climbs slopes by day, cool air cascades down valleys by night. Valley breeze, daytime sun heats mountain slopes, air rises, pulling air up valleys. Mountain breeze, at night slopes cool quickly, dense cold air sinks down into valleys, forming calm, chilly flows. These winds affect frost patterns, farming, and local weather. Trade winds, Earth's tropical conveyor belts. Steady, reliable, and once vital for explorers, trade winds are the steady currents that power weather and ocean journeys near the equator. Warm air rises at the equator, moves poleward high up, then sinks around 30 degrees latitude. This creates the Hadley cells, giant atmospheric loops. As air sinks, it flows back toward the equator, the trade winds. Blowing from the northeast in the northern hemisphere, southeast in the southern. These winds carried ships from Europe to the Americas for centuries. Westerlies, winds of the temperate zones. Between the tropics and the poles, the westerlies roar. Unpredictable yet vital for storms and jet streams. From 30 degrees to 60 degrees latitude, air moves from high to low pressure, deflected by Earth's spin. They blow from the west to the east, hence the name. Westerlies guide weather systems across North America and Europe. They make weather in temperate zones so changeable. Polar easterlies, icy outflows. At Earth's frozen edges, cold dense air sinks and flows outward, icy winds drifting from the poles. Air at the poles cools and sinks, creating high-pressure zones. It flows toward lower latitudes, deflected westward by the Coriolis effect. These frigid winds mix with the westerlies, stirring up polar fronts that spark storms. Jet streams, rivers of air. High above the ground, jet streams whip around the globe, invisible rivers steering storms and flights. Jet streams form where warm and cold air masses meet, usually at the boundaries between circulation cells. The strongest, the polar jet stream, about 9 to 12 kilometers up. They can blow at 160 kilometers per hour, 100 miles per hour or faster. Pilots use them to save fuel on west-east flights, but crossing them can mean turbulence. Monsoons, seasonal giants. Monsoons are more than rain. They're entire systems of seasonal winds that shape the lives of billions. In summer, land heats faster than ocean. Warm air rises over land, pulling in moist ocean air, bringing heavy rains. In winter, land cools quickly, reversing the flow. Dry winds blow from land to ocean. The Asian monsoon is the biggest, feeding rice paddies and forests, but also bringing floods if it's too strong. Local wind wonders, Chinooks, Santa Anas, and more. Winds can turn mild or wild, depending on where you live, from warm mountain gusts to bone-dry desert blasts. Chinook winds sweep down the Rockies, raising temperatures in hours. Santa Ana winds in California blow dry air through mountain passes, fanning wildfires. Sirocco winds carry Sahara dust into southern Europe. Each local wind has its story, shaped by land, sea, and the air's restless push. The power and peril of winds. Winds spread seeds, carry pollen, shape dunes, and fill sails. But they can also power storms that change history. Strong winds drive hurricanes and typhoons. Tornadoes are Earth's fiercest winds, spinning up to 300 miles per hour, 480 kilometers per hour. Wind erosion can wear down rocks or create fertile plains. Today, we harness winds for clean energy, spinning turbines that echo old sailing ships. Ocean currents, Earth's blue conveyor belts. The ocean's hidden rivers. Close your eyes and imagine the ocean not as a still blue blanket, but as a restless river of salt water, vast currents flowing for thousands of miles. Ocean currents are continuous flows of seawater driven by wind, Earth's rotation, and differences in water density. Some flow at the surface, others deep below. They move heat from the equator to the poles and help regulate global climate. Without them, the tropics would be hotter and the poles even colder. Surface currents, driven by winds. Feel the steady trade winds blowing across the sea. They drag the surface water with them, creating currents that circle the globe. Winds like the trade winds and westerlies push water along. The Coriolis effect bends these flows into vast gyres, circular systems of currents. There are 5 major ocean gyres: North Atlantic, South Atlantic, North Pacific, South Pacific, and Indian Ocean. These currents help transport warm and cold water, shaping local climates. Gyres, the ocean's whirlpools. Imagine giant spirals of water. Each gyre spins like a slow, vast whirlpool, guided by winds and Earth's spin. In the northern hemisphere, gyres spin clockwise, in the southern, counterclockwise. The North Atlantic gyre includes the Gulf Stream, a powerful warm current that warms Europe. Gyres also trap floating debris, forming garbage patches like the Great Pacific Garbage Patch. The Gulf Stream, a warm river in the sea. If you stood on a boat off Florida, you could feel the Gulf Stream, a river within the ocean, racing northward at up to 6 kilometers per hour, 3.7 miles per hour. The Gulf Stream carries warm water from the Gulf of Mexico up the eastern U.S. coast and across the Atlantic toward Europe. It helps keep Western Europe's climate milder than other places at the same latitude. Changes to the Gulf Stream could dramatically shift weather patterns. Upwelling, the ocean's nutrient elevator. Beneath the waves, currents sometimes rise, pulling up nutrients from the deep, feeding plankton, fish, and entire coastal communities. Upwelling happens when winds push surface water away from shore. Colder, nutrient-rich water rises to replace it. This process fuels some of the world's richest fishing grounds, like off Peru and California. Without upwelling, coastal ecosystems could collapse. Deep ocean currents, the global conveyor belt. Below the surface, slow, massive rivers of cold, salty water crawl through the deep, connecting every ocean in one vast loop. The thermohaline circulation moves water driven by differences in temperature, thermo, and salinity, haline. Cold, salty water is dense and sinks in places like the North Atlantic. This deep water flows around the world for centuries before rising again. It helps store carbon dioxide and heat, regulating Earth's climate over long timescales. El Niño and La Niña, the ocean's mood swings. Sometimes the ocean's surface currents shift their usual pattern, sending ripples through weather worldwide. El Niño warms the Pacific Ocean near the equator, changing winds and currents. This weakens upwelling, harming fisheries and changing rainfall patterns. La Niña does the opposite, strengthening trade winds, boosting upwelling, and shifting storms. These cycles can cause floods, droughts, and global temperature swings. How currents shape climate. Currents act like invisible highways for heat. Without them, the planet's climate would be wildly different. Currents distribute solar energy across the globe, balancing temperature extremes. They affect coastal climates. The California current cools the U.S. West Coast. The Gulf Stream warms northern Europe. Disruptions in these flows could shift weather patterns dramatically. Marine life and currents. Currents carry nutrients and life. Many sea creatures drift with these flows, from tiny plankton to giant sea turtles migrating thousands of miles. Plankton blooms often trace upwelling zones. Fish, whales, and seabirds follow currents to feed. Some species, like eels, use currents for their epic migrations. Coral reefs thrive where currents bring clear, nutrient-rich water, protecting the ocean's circulation. As Earth warms, melting ice and shifting winds could weaken the ocean's great conveyor belts. Scientists watch carefully, because our climate depends on it. Fresh water from melting glaciers can dilute salty water, making it less dense and slowing deep currents. Changes in the Gulf Stream or thermohaline circulation could trigger abrupt climate shifts. Pollution and plastic waste ride currents, collecting in gyres and harming marine life. Protecting ocean health protects the whole system that keeps weather and climate stable. Storms and extreme weather. The power of a storm. A calm day can turn wild in moments. Clouds gather, winds roar, and the sky unleashes its power. But what truly makes a storm so fierce? Storms form when warm, moist air rises and meets cooler air above. This collision creates instability, fueling powerful upward currents. The energy released by condensing water vapor powers clouds, winds, and rain. Thunderstorms are nature's pressure release valves, balancing energy in the atmosphere. Thunderstorms, nature's light show. Every bolt of lightning reminds us that the atmosphere is alive with energy, waiting to be discharged. Thunderstorms are common worldwide. About 1,800 happen every day. Warm air rises rapidly, cools, and forms towering cumulonimbus clouds. Inside, droplets and ice crystals collide, creating electrical charges. When the charge is strong enough, lightning flashes, the air explodes, creating thunder. Tornadoes, Earth's fiercest winds. In some storms, the winds spiral down into funnels that can tear buildings apart and toss cars like toys. Tornadoes form in severe thunderstorms where winds change direction and speed with height, creating spin. If the rotating air tilts vertically, a funnel cloud may touch the ground. The strongest tornadoes can have winds over 300 miles per hour, 480 kilometers per hour. The U.S. Great Plains, nicknamed Tornado Alley, sees more tornadoes than anywhere else. Hurricanes, ocean-born giants. Far out at sea, warm waters give birth to the largest storms on Earth, spiraling beasts that can span hundreds of miles. Hurricanes, or cyclones, typhoons, form when warm ocean water, over 26 degrees Celsius per 79 degrees Fahrenheit, evaporates rapidly. The Coriolis effect spins these rising columns of moist air into a rotating system. As they grow, they pull in more warm, moist air, fueling winds and rain. The eye is calm, but the eye wall holds the fiercest winds. Blizzards, winter's wrath. Not all storms roar with thunder, some blanket the world in white silence, shutting down cities and shaping landscapes. Blizzards combine heavy snow, fierce winds, and low visibility. Cold air masses collide with moist, warm air, snow forms and wind spreads it into whiteout conditions. The snow insulates the ground but can block roads and bury homes. Regions like the northern U.S., Canada, and Siberia know this icy power well. Hailstorms, ice from the sky. Sometimes thunderstorms grow so tall and cold that they forge hailstones, marble to softball-sized ice bombs that crash to Earth. Inside towering cumulonimbus clouds, strong updrafts lift raindrops high into freezing air. Droplets freeze, fall, get lifted again, and grow larger with each cycle. Once they're too heavy for the updraft, they drop to Earth. Hail can shred crops, dent cars, and break windows. Floods, when water overflows. Water gives life, but when too much comes too fast, it can sweep it away just as easily. Heavy rain, rapid snowmelt, or storm surges can cause floods. Rivers overflow their banks, streets become rivers, and farmland turns to lakes. Flash floods happen with little warning, especially in urban areas where water can't soak in. Floodplains are shaped and nourished by these events, but they put people at risk. Droughts, when rain stops coming. While some places drown, others thirst. Droughts creep in slowly, but their grip can last for years. Droughts occur when rainfall stays below normal for long periods. Crops wither, rivers dry up, and wildfires spark more easily. Heat waves can worsen droughts by evaporating what little moisture remains. Climate change is making some droughts longer and more severe. Heat waves and cold snaps. Sometimes the atmosphere locks in place, and what should pass lingers, cooking or freezing whole regions. Heat waves happen when high-pressure systems trap hot air over an area. Cities suffer worse because concrete and asphalt absorb heat, urban heat islands. Cold snaps can occur when the polar vortex, a ring of cold air around the poles, weakens and spills southward. Both can stress power grids, harm crops, and threaten lives. How extreme weather shapes us. Storms remind us that Earth's atmosphere is alive, and that our cities, farms, and plans must adapt to its moods. Communities build levees, storm shelters, and weather early warning systems. Farmers adapt crops to drought or flood-prone regions. Scientists study past weather events to predict future extremes. Understanding storms helps us prepare and respect the power above us. Fog, clouds, and mystical skies. The secret life of clouds. Look up. Every cloud is a fleeting sculpture, a clue to the moods of the sky. They drift, grow, vanish, like thoughts across the mind. Clouds form when warm air rises, cools, and water vapor condenses on tiny dust or salt particles. The shapes depend on temperature, moisture, and wind. Meteorologists read clouds like books. They reveal what weather might come next. Without clouds, Earth would lose heat too quickly at night. The major types of clouds. Cirrus, cumulus, stratus. Each name is like a character in the sky's great play. Cirrus, high, wispy ice crystal streaks, signal fair but changing weather. Cumulus, fluffy, white, fair weather clouds, the classic cartoon cloud. Stratus, low, blanket-like layers, bring gray skies and drizzle. Cumulonimbus, towering giants, thunderheads that produce storms. Learning to read these helps anyone predict what's next. The beauty of lenticular clouds. Some clouds are so unusual they look alien, like lenticular clouds, stacked like flying saucers over mountain peaks. Lenticular clouds form when moist air flows over hills or mountains and sets up standing waves. Air cools at the crest, forming clouds, sinks and warms in the trough, clearing them, making the lens shape. Pilots avoid them because they signal turbulent air. But they're a favorite for photographers and dreamers. Fog, clouds that touch the earth. Step into a foggy morning, you're walking inside a cloud. Familiar streets become mysterious, sound is muffled, the world feels smaller. Fog forms when air near the ground cools to its dew point, and water vapor condenses. Common types: radiation fog, clear, calm nights; advection fog, warm, moist air over cold surface; evaporation fog, cold air over warm water. Sailors and pilots fear fog for its blinding effect. But for many, it's peaceful and eerie, a natural hush. Mist versus fog, what's the difference? Fog and mist are siblings, the same at heart, just different in how they let you see the world. It's all about visibility. Fog reduces visibility to less than 1 kilometer, 0.6 miles. Mist lets you see a bit farther, up to 2 kilometers, 1.2 miles. Both add moisture to the air, cool the ground, and can help plants. They can transform a landscape into something magical. Dew and frost, the morning's gift. When the air is still and the night is clear, the earth breathes out its warmth, and tiny droplets gather like jewels on grass and leaves. Dew forms when objects cool below the dew point and moisture condenses. On freezing nights, water vapor can skip the liquid stage and deposit as frost. Dew and frost reduce evaporation loss and can hydrate plants in dry climates. They're tiny reminders of the air's constant cycle of moisture. Rare wonders: virga and fall streak holes. Sometimes the sky plays tricks. Rain falls but evaporates before hitting the ground, a ghostly trail called virga. Virga happens in dry air, often in deserts. It cools the air beneath, sometimes creating downdrafts or gusts. Fall streak holes, or hole punch clouds, appear when ice crystals form in supercooled clouds, making a circular gap. These phenomena show how dynamic and fleeting the atmosphere really is. Halos and sundogs, ice crystals at work. On cold days, the sun may wear a halo or grow twin rainbow-colored dogs on either side, wonders crafted by ice in the upper air. Cirrus clouds contain millions of ice crystals that refract sunlight. Halos are rings around the sun or moon, a sign of moisture high up. Often a storm is coming. Sundogs appear as bright spots flanking the sun, common when the sun is low. These optical wonders remind us that the atmosphere is a giant prism. Fog in culture and myth. For centuries, fog has symbolized mystery, danger, and transformation, a curtain hiding what lies ahead. Sailors feared fog for hiding reefs and rival ships. In literature, fog often marks a turning point, a hero lost or a truth revealed. Folklore tied fog to spirits or ghosts, the world between seen and unseen. Even today, a foggy morning can feel like stepping into a dream. Why clouds and fog matter. Beyond the beauty, clouds and fog help keep Earth's climate in balance, shading us from the sun, trapping warmth, watering the land. Clouds reflect sunlight, albedo effect, and insulate heat at night. Fog adds moisture where rain is rare. Changes in cloud cover influence global temperatures. Scientists study clouds to improve weather predictions and understand climate change. Rainbows, lightning, and atmospheric phenomena. How rainbows are born. A rainbow is sunlight taking the long way around, bending, bouncing, and spreading into colors that arch across the sky. Rainbows form when sunlight enters a raindrop, slows down, bends, refraction, reflects inside the drop, and bends again as it exits. Each color bends slightly differently. Red bends the least, violet the most. This spreads white light into its spectrum. The shape is always a full circle, but we usually see just an arc because the ground blocks the rest. Double rainbows and supernumerary bows. Sometimes the sky surprises us with more than one rainbow, faint twins or extra pastel bands stacked like secret whispers. A double rainbow happens when light bounces twice inside the raindrop before exiting. The second bow is fainter and the colors reverse, red inside, violet outside. Supernumerary bows are extra pastel bands caused by very tiny, uniform droplets. These delicate rainbows remind us that even common sights hold layers of wonder. Moonbows, lunar rainbows. Imagine a rainbow at night, pale and ghostly, born of moonlight instead of sunlight. Moonbows are rare because the moon must be bright and full, with rain opposite it in the sky. They are fainter than daytime rainbows because moonlight is weaker. Sometimes they appear white to the naked eye, but cameras can capture their subtle colors. Waterfalls like Yosemite's Bridal Veil Falls are famous for moonbows. Sundogs, halos, and light pillars. The atmosphere is full of tiny ice crystals. When the light catches them just right, the sky wears a crown of halos and rainbow spots. Sundogs, parhelia, appear as bright spots flanking the sun, often with a halo around it. Halos are rings formed when ice crystals bend light 22 degrees. Light pillars appear when light reflects off ice crystals near the ground, creating vertical beams. These effects are common in cold climates, gifts for keen eyes on frosty mornings. The dance of lightning. Lightning is nature's instant energy release, an electric handshake between sky and earth, or cloud to cloud. Within a storm cloud, ice particles collide, building up opposite charges. The difference grows until the air can't insulate it anymore. A bolt forms, superheating the air to 30,000 degrees Celsius, 54,000 degrees Fahrenheit. The rapid expansion causes thunder. A single bolt can light a 100-watt bulb for 3 months. Types of lightning, more than just a flash. Not all lightning strikes the same. Some crawls across the sky, some flickers within clouds, and some even shoots up. Cloud to ground is the most familiar, the classic strike. Cloud to cloud lightning stays high, illuminating the sky. Sheet lightning lights up clouds like a lantern. Anvil crawlers sprawl like electric fingers. Sprites and jets are rare high-altitude discharges reaching into the upper atmosphere, a reminder of the sky's layered mystery. St. Elmo's fire, ghostly glow. Sailors and pilots once whispered about St. Elmo's fire, a blue or violet glow on masts and wingtips, like tiny spirits dancing. It's not fire, but a plasma discharge. A strong electric field ionizes air, creating a faint glow. It often happens during thunderstorms, especially on pointed objects like ship masts or airplane noses. To ancient mariners, it was a sign of protection or warning from the storm. It shows how electricity naturally builds up and finds paths to discharge. Ball lightning, the elusive orb. Ball lightning is one of weather's strangest tales, glowing spheres drifting silently before vanishing in a flash. Rare and not fully understood, ball lightning has been reported during storms for centuries. Witnesses describe floating orbs the size of a grapefruit or larger, lasting a few seconds. Some theories, microwave bubbles, burning silicon particles, or plasma. Its fleeting nature makes it hard to study, but it reminds us the sky still keeps secrets. Auroras, Earth's polar light show. Near the poles, the sky dances with color, green, red, purple curtains of light that ripple in silence. Auroras happen when charged particles from the sun hit Earth's magnetic field and collide with gases in the upper atmosphere. Oxygen glows green or red, nitrogen gives blue or purple hues. The aurora borealis lights the Arctic, while the aurora australis glows in the Antarctic. These lights remind us that space weather and Earth's atmosphere are forever entwined. Chasing the wonders of the sky. Rainbows, lightning, auroras, each fleeting show in the sky is a reminder of nature's hidden artistry. All you have to do is look up. Ancient cultures saw signs and stories in these lights. Scientists study them to understand electricity, particles, and our magnetic field. Photographers travel the world to catch the rarest displays. Even today, one rainbow can lift the spirits, a reminder that beauty can appear when least expected. Weather versus climate, what's the difference? Every raindrop, every breeze, every sunny day is a piece of weather. But climate is the grand pattern behind it all, the canvas on which weather paints. Weather is short-term, hours, days, even weeks. Climate is the average weather patterns over decades and centuries. You might have a cold day during a warming trend. That doesn't mean the climate isn't changing. Understanding the difference helps us see why single storms don't tell the whole story. Earth's greenhouse blanket. Our atmosphere is like a quilt. It keeps enough heat in to make life possible. But when that blanket thickens too much, it traps too much warmth. Greenhouse gases like carbon dioxide, methane, and water vapor trap heat radiating from Earth's surface. Without this effect, Earth would be frozen, about -18 degrees Celsius 0 degrees Fahrenheit. Human activities, especially burning fossil fuels, add more CO2 than natural cycles can handle. The result, a slowly warming planet. How a warmer world changes weather. Think of the atmosphere as a giant pot of soup. Add more heat, and it bubbles more violently. Warmer air holds more moisture, fueling heavier rains and more intense storms. Heat waves become longer and hotter. Some regions get wetter, others drier. Storm tracks may shift. Hurricanes can become stronger and move differently. Melting ice and rising seas. High in the Arctic, ancient ice sheets crack and melt. Glaciers shrink. Sea ice thins. All this water has to go somewhere. Melting glaciers and ice sheets add fresh water to oceans, raising sea levels. Warmer water expands, adding to the rise. Coastal cities face more flooding, erosion, and storm surge damage. Small island nations may disappear altogether without protective action. Changing currents, changing climates. Remember the ocean's conveyor belts? Warming and melting ice can disrupt these flows, with huge consequences. Cold, salty water in the North Atlantic drives deep ocean currents. Too much fresh meltwater can reduce salinity, weakening this flow. If currents slow, regions like Europe could see colder winters, even in a warming world. It's a delicate system that links ice, water, and winds. Droughts and floods, extremes becoming normal. A hotter atmosphere swings between too dry and too wet. Some fields crack with drought while others drown under floods. Climate change shifts weather patterns, longer dry spells, intense rainfall, flash floods. Farmers struggle as growing seasons shift and water becomes unpredictable. Reservoirs dry up, then overflow. Adaptation means learning to handle bigger swings in water supply. Wildfires and heat waves. Dry forests turn to tinder. A lightning strike, or spark from a power line, and an inferno races across the land. Hotter temperatures dry out vegetation, creating more fuel for fires. Some places see longer fire seasons. Heat waves stress cities, power grids fail, health risks rise. Urban heat islands trap warmth, making nights dangerously hot. How climate affects human health. Our lungs breathe what the air holds. Our bodies feel every heat wave, every flood, every shifting season. Air pollution worsens in heat, more ozone, more asthma. Changing climates bring new pests and diseases to areas that never saw them before. Extreme heat kills more people each year than many realize. Communities with fewer resources suffer the most. Seeing the signs, how we know it's real. Ice cores, tree rings, satellite images. The Earth keeps its own diary, if we know how to read it. Scientists measure rising CO2 in the atmosphere and oceans. They track retreating glaciers, shrinking Arctic ice, and migrating species. Tree rings and corals show past climate swings. The evidence is clear. Earth's average temperature is rising faster than natural cycles can explain. Hope, what we can do. Though the challenge is huge, the future isn't fixed. Every action to reduce emissions and protect nature helps write a better story. Renewable energy cuts carbon pollution at the source. Forests, wetlands, and healthy oceans soak up CO2 naturally. Communities adapt with better flood defenses, green roofs, and drought-resistant crops. Small changes, multiplied across billions of people, add up. Understanding climate helps us protect the weather patterns that make Earth our home. Ecosystems and weather. The living weather machine. Step into a rainforest, a prairie, or a tundra. Each is its own tiny world, breathing water, heat, and gases back into the air. Ecosystems help regulate local weather. Forests transpire. Trees pull water from soil and release it as vapor, adding humidity and even forming rain clouds. Grasslands absorb and release heat differently than forests, influencing wind and storm paths. Wetlands store water during floods and release it during droughts. Rainforests, the Earth's green lungs. In the Amazon, billions of trees inhale carbon dioxide and exhale moisture. The forest creates its own rain. Trees pull up groundwater and release it through their leaves in a process called transpiration. This keeps the air humid and fuels daily rainstorms. When rainforests are cut down, local rainfall drops, and droughts become more common. Rainforests are critical for stabilizing both regional weather and the global climate. Deserts, life in extremes. A desert may look lifeless, but its plants and animals are experts in surviving heat waves and dry winds. Deserts have dramatic weather shifts, scorching days, freezing nights. Cacti store water and open pores at night to avoid daytime heat loss. Desert animals burrow or come out at dawn and dusk. Winds shape dunes, spread seeds, and carry dust that fertilizes rainforests thousands of miles away. Oceans, the climate's beating heart. Under the waves, currents move like rivers, carrying warmth, nutrients, and life across the globe. Plankton blooms cool the ocean surface and affect how much CO2 the sea absorbs. Coral reefs create calm, shallow areas that influence wave patterns and protect coasts from storms. Marine animals like whales store nutrients as they dive, helping tiny plants thrive. The ocean's living systems help drive rainfall on land. Wetlands, nature's sponges. Where land meets water, wetlands soak up floodwaters, filter pollution, and cool the air. Marshes and swamps hold extra rain during storms, slowing floods. Plants and soil clean water before it reaches rivers. Wetlands release stored moisture during dry spells, stabilizing local weather. Destroying wetlands means higher flood risks and less natural water storage. Forests beyond the rainforest. Temperate forests, boreal forests, all of them breathe moisture and shelter countless species that adapt to every season. Deciduous forests shed leaves to survive cold winters, changing the way they interact with snow and sun. Boreal forests store carbon in trees and frozen soils. If they thaw, they release greenhouse gases. Forest fires, natural or human-caused, can change regional weather by releasing smoke and soot. Healthy forests moderate temperatures and provide steady rainfall. Mountains, weather makers and barriers. Mountains stand like ancient guardians, forcing winds up, catching rain and snow, casting rain shadows. When moist air hits a mountain, it rises, cools, and drops rain or snow, creating lush slopes on one side and dry regions on the other. Mountain forests trap snowpack that melts in spring, feeding rivers. Alpine plants and animals adapt to thin air and sudden storms. As climate warms, snow lines rise, affecting fresh water for millions. Animals that shape weather. Bees pollinate plants that keep forests alive. Elephants knock down trees, shaping savannas. Tiny creatures have big effects. Herds of grazing animals keep grasslands open, which affects how the land absorbs heat and rain. Beavers build dams, creating wetlands that cool local air and store water. Whales store nutrients as they feed, boosting plankton that helps absorb CO2. Even locusts and termites influence vegetation, soil, and humidity. When ecosystems collapse, weather goes wild. If forests burn or dry up, if oceans warm too fast, the balance tips. The weather shifts in ways we're just starting to understand. Deforestation can turn moist regions into dry savannas. Coral bleaching reduces coastal protection, letting storms hit harder. Loss of wetlands increases flooding and heatwaves. Protecting ecosystems keeps local weather more stable. Nature's blueprint for the future. By studying how ecosystems shape weather, we find clues for how to adapt: more green spaces in cities, restored wetlands, healthy forests. Urban forests and green roofs cool cities and reduce flooding. Protecting mangroves buffers coasts from hurricanes. Sustainable farming keeps soil healthy, reducing dust storms. Nature teaches us that resilience depends on diversity. The more varied life is, the more stable weather can be. Weather's impact on human history. The climate behind ancient civilizations. From Mesopotamia's Fertile Crescent to the lush banks of the Nile, steady rains and predictable floods gave birth to agriculture and the first cities. Early civilizations depended on rivers fed by seasonal rains. The Nile's annual flooding deposited rich silt, making Egypt's crops flourish. Mesopotamia thrived between the Tigris and Euphrates until droughts and salinization weakened fields. The Indus Valley civilization likely collapsed in part due to shifting monsoons and river courses. The Dust Bowl, when weather made migrants. In the 1930s, the American plains turned to dust, farms failed, skies darkened, and millions fled their homes in search of rain. Overfarming and poor soil management left topsoil exposed. Years of drought turned the soil to fine dust that blew in massive storms. Black blizzards buried homes, suffocated livestock, and blocked sunlight. The Dust Bowl forced new farming practices and shaped migration to California. The Little Ice Age, centuries of chill. From the 1300s to the mid-1800s, Europe and parts of North America shivered through colder-than-average winters, rivers froze, crops failed, and cultures adapted. Shorter growing seasons led to famines and population declines. The Thames River in London froze so solid that people held frost fairs on the ice. Cold weather encouraged new innovations, better insulation, warm clothing, and food storage. Some empires weakened as harvests shrank and people moved in search of warmth. Storms that changed battles. History is full of wars lost or won by sudden storms, when the weather turned into an invisible ally or enemy. In 1588, the Protestant wind, fierce storms, scattered the Spanish Armada, protecting England. Napoleon's march into Russia was devastated by the brutal winter of 1812. D-Day in World War II depended on a break in the stormy English Channel. One clear day changed history. Weather remains a hidden factor in military planning today. Monsoons and empires. For centuries, the Indian Ocean's monsoon winds were the engine of trade and culture. Ancient sailors learned to ride seasonal winds to trade spices, silk, and precious metals. Civilizations flourished where monsoons brought dependable rain for crops. Failure of monsoons led to famine, migration, and political upheaval. Modern climate change is making monsoon timing less predictable. Droughts that toppled kingdoms. A few years of missing rain can topple kings. A single dry decade can erase a city from maps. The Mayan civilization's collapse coincided with long periods of severe drought. In China's history, droughts sparked peasant revolts that toppled dynasties. The Dust Bowl showed how modern nations are still vulnerable. Droughts test food security and push communities to adapt, or move. Flood myths and memory. From Noah's Ark to ancient Sumerian legends, great floods appear in the oldest human stories, echoes of real disasters etched in memory. Many cultures have myths about floods that destroyed old worlds and cleansed the earth. Archaeologists believe some stories reflect real river floods that reshaped ancient settlements. Floods bring destruction but also renewal. Rivers deposit rich soil for crops. Modern levees and dams try to tame floods but sometimes fail dramatically. Weather in art, culture, and religion. Storms, rainbows, and droughts appear in our oldest paintings, poems, and prayers, reminders that weather shapes more than crops. Ancient people worshipped rain gods and sun gods to protect harvests. Japanese haiku often celebrate fleeting rain or snow. Medieval artists painted biblical floods as warnings. Even today, weather metaphors color our language. Storms of change, calm before the storm. Modern disasters, lessons from history. Hurricanes Katrina and Sandy, wildfires in Australia and California. Extreme weather still tests our cities and our compassion. Modern forecasting helps, but powerful storms still displace millions. Cities learn from history, better levees, fire breaks, evacuation plans. Climate change adds urgency, sea level rise, stronger hurricanes, longer droughts. The past reminds us that preparation saves lives. The future, writing our own weather story. How we live today will decide what weather means for tomorrow's children. Will they read our time as caution or inspiration? Communities are planting trees, restoring wetlands, and building smarter. Cities. Scientists learn from ice cores, tree rings, and old diaries to predict the future. Renewable energy, sustainable farming, and resilience planning give hope. We are weather's children, and its guardians. Weather forecasting, the science of prediction. The birth of weather lore. Long before satellites and radar, farmers and sailors looked to the sky for signs, red sunsets, rings around the moon, swallows in flight. Ancient cultures connected cloud shapes, winds, and animal behavior to tomorrow's weather. Proverbs like, "Red sky at night, sailors' delight," still echo old observations about high-pressure systems. Some folk sayings have real science behind them, while others are just myths. Early weather lore was humanity's first forecasting tool. From barometers to thermometers. When people learned to measure air pressure and temperature, they found hidden patterns that the eye alone could not see. In the 1600s, Galileo's students invented the thermometer. Evangelista Torricelli invented the barometer, showing how air pressure changes with weather. High pressure often brings clear skies. Falling pressure hints at storms. These simple tools laid the groundwork for modern forecasting. Telegraphs and the first forecasts. In the 1800s, a message could outrun the storm itself. The telegraph made weather maps possible. Before the telegraph, storms would hit without warning. Meteorologists could now share observations from faraway cities in real time. In 1861, Robert Fitzroy created the first daily weather forecasts for newspapers in England. Some people mocked the forecasts, but many lives at sea were saved. Weather stations, watching the world. Today, thousands of tiny outposts measure wind, rain, heat, and pressure, all feeding the great forecasting machine. Weather stations span mountaintops, deserts, cities, and oceans. They collect hourly data on temperature, humidity, and wind speed. This information goes into huge models that simulate Earth's atmosphere. Without local data, global predictions would be impossible. Radar, seeing inside storms. Radar is like X-ray vision for weather. It shows where rain falls, how hard it hits, and how it moves. Radar bounces radio waves off raindrops or snowflakes. Doppler radar detects rotation inside storms, helping predict tornadoes. Weather radar shows precipitation in real time, allowing precise local warnings. Pilots, farmers, and emergency crews rely on radar images daily. Satellites, the eyes in space. From orbit, satellites watch hurricanes swirl, clouds grow, and see ice shrink, a view no human could ever see alone. Weather satellites track huge systems like typhoons and jet streams. Some measure cloud heights, temperatures, and moisture content. Others monitor Earth's energy balance and greenhouse gases. Satellites forecasting by giving us a complete global picture. Supercomputers and weather models. Every forecast is a puzzle solved by math, equations running on supercomputers that simulate the atmosphere hour by hour. Forecast models divide Earth into millions of grid cells. They calculate how heat, moisture, and wind move between cells. More powerful computers mean more detail and better accuracy. Even the best models face chaos. The butterfly effect means tiny errors can grow. Warnings and watches, saving lives. A tornado siren, a hurricane evacuation, a flood alert. Forecasting turns knowledge into action. Meteorologists issue watches when conditions are right and warnings when danger is imminent. Early warnings give people time to evacuate or take shelter. Better forecasts have drastically reduced deaths from hurricanes and typhoons. Communication is key. Forecasts must reach everyone in time. The limits of forecasting. Weather is a dance of chaos. Some moves we can predict, some surprise us no matter how much we watch. Short-term forecasts, 1 to 3 days, are very reliable now. Medium-term forecasts, 5 to 10 days, get trickier as small errors grow. Long-range seasonal outlooks depend on ocean patterns like El Niño. Despite our technology, nature still keeps secrets. The future, smarter, faster, closer. AI, better satellites, and crowdsourced data will shape the next generation of weather forecasting. Machine learning can spot patterns humans might miss. Tiny CubeSats provide more frequent updates from space. Weather apps let people report conditions in real time. As climate change brings wilder extremes, better forecasting will help communities adapt. Extreme weather events. Hurricanes, giants of the ocean. Imagine warm ocean water feeding a spinning beast the size of entire countries. A hurricane is nature's engine at its fiercest. Hurricanes, or cyclones, typhoons, form over warm tropical oceans where sea temperatures exceed 26 degrees Celsius (79 degrees Fahrenheit). Warm, moist air rises, creating low pressure below, more air rushes in and spins due to Earth's rotation. They grow stronger if they stay over warm water. Land and cold water weaken them. Their winds, rains, and storm surges can reshape coastlines overnight. Tornadoes, twisters of the plains. A tornado is a spinning column of air that drops like a finger from thunderclouds, powerful, sudden, and terrifyingly precise. Tornadoes form inside severe thunderstorms, especially in Tornado Alley, in the U.S. Warm, humid air at the surface collides with cooler, drier air above, creating instability. If winds at different altitudes blow at different speeds and directions, rotation begins. Tornadoes can have winds over 300 miles per hour, yet the path may be only a few miles long. Heat waves, the silent killers. Invisible, relentless, and often underestimated, heat waves kill more people than any other extreme weather. A heat wave is a prolonged period of excessive heat, often with high humidity. Urban heat islands make cities even hotter than rural areas. Nights that stay warm are especially dangerous because the body can't recover. Climate change is making heat waves longer, hotter, and more frequent. Flash floods, when water turns wild. A single downpour can transform a peaceful street into a raging river in minutes. Flash floods are sudden and ruthless. Occur when heavy rain overwhelms the ground's ability to absorb water. Urban areas with lots of concrete are especially vulnerable. Steep, dry terrain, like desert canyons, can become deadly flood channels. Warning systems and good drainage save lives, but sometimes water comes too fast. Droughts, the slow disaster. No thunder, no roar. Just empty rivers, cracked earth, and crops that wither under a merciless sun. Drought is a prolonged lack of rain that depletes soil moisture and water supplies. It can creep up slowly, sometimes going unnoticed until reservoirs run dry. Droughts can ruin harvests, trigger wildfires, and force migrations. Climate patterns like El Niño can intensify or prolong droughts. Hailstorms, ice from the sky. Picture stones of ice falling from towering storm clouds, denting cars, shattering windows, stripping leaves from trees. Hail forms when strong updrafts lift raindrops high into cold parts of the storm cloud. Droplets freeze, fall, get lifted again. Each trip adds more layers of ice. Hailstones can grow to the size of baseballs or larger. Hail damages crops, vehicles, roofs, and sometimes injures people and livestock. Lightning, nature's fireworks. A single bolt can light up the sky and split a tree in half, a breathtaking reminder of weather's raw power. Thunderstorms create areas of positive and negative charge. When the difference is big enough, electricity discharges in a flash of lightning. Thunder is the shockwave of heated air expanding rapidly. Lightning strikes start wildfires, damage power grids, and are one of the deadliest storm hazards. Superstorms and mega events. Sometimes systems collide in unexpected ways, blizzards with hurricane-force winds, or atmospheric rivers that flood entire regions. Superstorms aren't a formal category but describe unusually intense weather events. The 1993 storm of the century combined blizzard conditions with hurricane-force winds. Atmospheric rivers, long, narrow bands of moisture, can dump massive rain on coasts. As the climate warms, scientists watch for more of these extreme hybrids. Facing the fury, how we adapt. Even the fiercest storm has lessons: build smarter, prepare better, and respect nature's power. Early warning systems, shelters, and building codes save lives in tornado and hurricane zones. Heat action plans and urban trees help cities cope with rising temperatures. Flood control measures, levees, wetlands, green roofs, reduce flash flood risks. Studying extremes helps us face a world where record events become more common. The physics and chemistry of weather. The air we breathe, a moving fluid. We walk through it, we breathe it, yet we hardly feel its weight. Air is a swirling, flowing ocean of molecules. Earth's atmosphere is mostly nitrogen, 78%, and oxygen, 21%, with tiny amounts of water vapor, CO2, and trace gases. Air behaves like a fluid. It flows, rises, sinks, and carries heat. Air pressure is the weight of this column above us. It shapes winds and weather systems. Even small temperature differences set huge masses of air in motion. Heat transfer, conduction, convection, and radiation. Weather is the story of heat moving around, through the ground, the sea, and the sky. Conduction, heat travels through direct contact, like warm soil warming the air just above it. Convection, warm air rises, cools, and sinks, driving winds and storms. Radiation, Earth absorbs sunlight and radiates heat back as infrared energy. The balance of these transfers sets up weather patterns big and small. The greenhouse effect, Earth's thermal blanket. A thin veil of gases keeps our world warm enough for life, but too much or too little tips the scales. Greenhouse gases, like CO2, methane, water vapor, trap heat in the atmosphere. Without this blanket, Earth would be frozen and lifeless. Too many greenhouse gases amplify warming. More heat stays in, changing weather patterns. This balance shapes global climate, but also local extremes. The water cycle, molecules on the move. A single water droplet may evaporate from the ocean, ride a cloud across continents, fall as rain, then seep into soil, endlessly recycling. Evaporation pulls water into vapor form, storing heat energy. Condensation releases that heat, fueling storms and cloud formation. Precipitation returns water to Earth, rain, snow, sleet, hail. Transpiration from plants also feeds the cycle. Winds, pressure, and Coriolis dance. Why does the wind blow? It's air racing from high-pressure places to low, but the spinning Earth adds a twist. Air moves from areas of higher to lower pressure. Earth's rotation causes the Coriolis effect, curving winds to the right in the northern hemisphere, left in the southern. This gives us trade winds, westerlies, and swirling cyclones. Jet streams, fast rivers of air high up, guide storms and cold fronts. Clouds, chemistry in the sky. Every fluffy cloud is billions of droplets clinging to dust, salt, or pollen, chemistry drifting on the wind. Water vapor condenses on tiny particles called cloud condensation nuclei. Droplets collide, grow, and sometimes freeze into ice crystals. The shape and type of clouds depend on temperature, humidity, and wind. Clouds reflect sunlight and trap heat, moderating Earth's temperature. Thunderstorms, electric engines. Thunderheads are towering power plants, heat, water, and electric charge all wrapped into one rolling giant. Warm, moist air rises rapidly, cooling and condensing to build massive cumulonimbus clouds. Inside, updrafts and downdrafts create turbulence. Water droplets and ice rub together, building static charges. When the charge difference grows too big, lightning discharges it. Chemistry of rain, clean and not so clean. Each raindrop carries more than water. It gathers gases, dust, and sometimes pollutants on its way down. Natural rainwater is slightly acidic due to CO2 mixing with water to form carbonic acid. Industrial pollution can create acid rain, harming forests and lakes. Rain cleans the air by bringing down dust and particles. Scientists study rain chemistry to understand local pollution. Microphysics, droplets, ice, and crystal ballet. Look closer. Storms form from trillions of tiny collisions and freezes, a ballet of molecules. Droplets bump into each other, coalescing into bigger drops that fall as rain. In cold clouds, ice crystals form around tiny particles, then grow as they collect supercooled water. Bergeron process. In mixed clouds, ice grows at the expense of water droplets, creating snowflakes. Understanding microphysics helps improve rainfall predictions. The butterfly effect, chaos theory and forecasting. A butterfly flaps its wings in Brazil and sets off a tornado in Texas, or so the saying goes. Small changes in initial conditions can cause wildly different outcomes. Edward Lorenz discovered this when he reran weather models with tiny rounding differences. This is why long-term weather forecasts have limits. Chaos is built into the atmosphere. Embracing uncertainty helps forecasters prepare for multiple scenarios. Climate change and the future of weather. The greenhouse blanket gets thicker. For millions of years, greenhouse gases have warmed Earth just right, but today, we're adding extra layers to the blanket. Carbon dioxide, methane, and other greenhouse gases trap heat in Earth's atmosphere. Burning fossil fuels and deforestation increase these gases, thickening the insulating layer. More trapped heat means global temperatures rise. A tiny global average shift means huge changes in weather extremes. Even 1 to 2 degrees Celsius makes hurricanes stronger, heat waves longer, and rainfall more intense. Oceans, the world's heat reservoir. The oceans soak up over 90% of excess heat, but warm seas change the weather we feel on land. Warmer oceans feed hurricanes and typhoons, giving them more energy to grow. Changing sea surface temperatures shift currents like the Gulf Stream. Coral reefs bleach when water temperatures climb too high, disrupting ecosystems. Rising sea levels from melting ice sheets add to storm surges and coastal flooding. Polar meltdown, ice, albedo, and feedback loops. White ice reflects sunlight. When it melts, darker ocean or land absorbs more heat, melting even more ice. This is called a positive feedback loop. Warming begets more warming. Arctic sea ice has shrunk dramatically in recent decades. Melting permafrost releases trapped methane, a potent greenhouse gas. These shifts affect global circulation patterns, like the jet stream. Heat waves, the new normal. Heat waves are growing longer, hotter, and deadlier, especially in cities where concrete traps warmth overnight. High-pressure systems lock in heat, creating stagnant, scorching air masses. Urban heat islands make nighttime temperatures stay high, stressing bodies. Vulnerable populations, the elderly, children, outdoor workers, face the biggest risks. Climate adaptation plans now include cooling centers, urban trees, and reflective roofs. Storms on steroids, more intense extremes. Warmer air holds more moisture. When it lets go, rainfall can break records overnight. Scientists see signs that hurricanes intensify faster than they used to. Rain bombs, sudden, massive downpours, are more common. Tornado patterns may shift as temperature contrasts change in the atmosphere. Extreme weather once considered rare may become more frequent. Droughts and water stress. Even as floods grow more intense, some regions dry out faster, rain comes all at once or not at all. Warmer air speeds up evaporation, drying out soils. Snowpack in mountains melts earlier, affecting rivers and reservoirs. Farmers face longer dry spells punctuated by flash floods that don't soak in. Water shortages can fuel migration, conflict, and economic strain. Wildfires, a fiery feedback loop. Heat dries forests, drought weakens trees, and a single spark can unleash an inferno. Many regions are seeing longer fire seasons. Climate change combines with land management issues to fuel megafires. Smoke from fires affects air quality far from the blaze. Burned forests release carbon, adding to warming, another feedback loop. Changing seasons, earlier springs, unpredictable winters. Plants bloom sooner, animals migrate at odd times, and humans must adapt to shifting patterns. Earlier spring melt can cause floods if ground is still frozen. Some species can't adjust fast enough, leading to mismatches in food supply. Warmer winters may reduce snowpack, affecting water for farms and cities. Seasonal diseases like tick-borne illnesses expand as climates warm. Climate models peeking into tomorrow. Powerful computers run thousands of scenarios to guess how today's choices shape tomorrow's skies. Climate models test different levels of emissions to predict temperature, rainfall, and storms. They're not perfect, but they show clear trends if emissions don't slow down. Models help cities and countries plan for resilient infrastructure and crops. The better we understand the atmosphere's chaos, the smarter our choices become. Hope and action, weathering the change. Though the forecast holds challenges, human creativity, science, and care for each other can change the story's ending. Renewable energy cuts greenhouse gas emissions at the source. Reforestation pulls carbon back out of the air. Early warning systems, stronger buildings, and better planning help communities adapt. Each choice, by governments and everyday people, is a ripple in Earth's weather story. Weather around the world. Tropical rainforests. Wet, lush, and ever-changing. In the heart of the tropics, rain comes nearly every day, warm, gentle, then wild. A forest canopy feeds the clouds that nourish it in return. Equatorial regions get intense sunlight year-round, fueling constant evaporation. Humid air rises, cools, and condenses into daily thunderstorms. Trees themselves help drive rainfall by transpiring moisture. The Amazon and Congo basins are Earth's lungs, weather makers for whole continents. Monsoon regions, the rhythm of wet and dry. A single wind shift can bring months of rain or weeks of parched silence. The monsoon is nature's seasonal heartbeat. Monsoons are seasonal wind reversals driven by temperature differences between land and ocean. South Asia's monsoon brings life-giving rain for rice crops, but also floods. East Asia, parts of Africa, and northern Australia have their own monsoon patterns. Climate change can make monsoons less predictable, swinging from drought to deluge. Deserts. Scorching days, freezing nights. In deserts, the air is dry and skies are clear, sun scorches by day, heat escapes by night. Lack of moisture means little cloud cover to trap heat or block sunlight. Temperatures can swing 30 degrees Celsius or more between day and night. Some deserts, like the Atacama, may not see rain for years. Wind-blown dust from deserts can travel thousands of miles, even feeding plankton in distant oceans. Savannas and grasslands, fires and storms. Between jungle and desert lies the savanna, where tall grasses sway under seasonal rains and lightning sparks wildfires. Savannas have distinct wet and dry seasons. Grasses grow rapidly with rain, then dry out, fueling natural fires that maintain the ecosystem. Thunderstorms can be dramatic, huge envel clouds rolling across open plains. Africa's Serengeti, the North American prairie, and Eurasian steppes all share this pattern. Temperate zones, 4 seasons in balance. Here, the weather dances between warm and cold, calm and wild. The beauty of spring flowers, summer storms, crisp autumn winds, and snowy winters. Mid-latitude regions have strong seasonal contrasts. Jet streams guide low-pressure systems that bring varied weather. Deciduous forests lose their leaves to survive winter's chill. These zones are often home to big cities. Forecasting is vital here. Mediterranean climates, sun-drenched and mild. Olive groves and vineyards thrive under hot, dry summers and mild, rainy winters, the perfect recipe for coastal living. Found along the Mediterranean Sea, parts of California, Chile, South Africa, and southern Australia. Summers dominated by subtropical high-pressure systems that block rain. Winters bring westerly winds and storms from the ocean. Wildfires are a natural, but increasingly dangerous, part of this climate. Polar regions. Frozen kingdoms of ice and wind. At Earth's edges, the air is so cold it crackles, blizzards swirl across tundra and glaciers calve into frigid seas. The Arctic and Antarctic are deserts in disguise. Little precipitation falls here. Sea ice expands in winter, shrinks in summer, changing weather far beyond the poles. Polar vortex, a strong upper-level wind pattern that can spill cold southward. As ice melts, these regions warm faster than anywhere else. Mountains, the weather makers. Mountains bend winds, trap clouds, and wring out rain, creating dry shadows and lush valleys side by side. When moist air hits a mountain, it rises, cools, and drops its moisture as rain or snow. The leeward side often stays dry, the rain shadow effect. Mountains can create microclimates with unique plants and animals. High peaks generate their own storms. Climbers must watch for sudden blizzards. Islands and coasts, life at the edge. Where land meets sea, breezes and tides shape daily life. Salt spray in your hair, thunderheads forming just offshore. Water heats and cools more slowly than land, moderating coastal temperatures. Sea breezes blow inland during the day. Land breezes return at night. Islands in the tropics often get daily afternoon storms. Hurricanes, typhoons, and tsunamis test coastal resilience. Urban weather, cities make their own climate. Concrete and glass trap heat, asphalt channels floods, cities are tiny weather machines, reshaping the air around them. Urban heat islands keep cities warmer than surrounding countryside. Tall buildings redirect winds and create updrafts that can form mini thunderstorms. Air pollution changes cloud formation and rainfall patterns. Greener cities, parks, green roofs, help soften these effects. The secret life of winds. What is wind? The breath of the planet. Feel the breeze on your face. That's air moving from one place to another, always seeking balance. Wind is air flowing from high pressure to low pressure areas. Temperature differences create pressure differences. The bigger the gradient, the stronger the wind. Winds constantly redistribute heat and moisture around the Earth. The Coriolis effect, spinning the winds. If Earth didn't spin, winds would blow straight, but our turning planet bends them into graceful curves. Earth's rotation deflects moving air to the right in the northern hemisphere, left in the southern. This effect shapes trade winds, westerlies, and polar easterlies. It's why hurricanes spin counterclockwise up north and clockwise down south. Without the Coriolis effect, weather patterns would be far simpler. Trade winds, the tropical engines. Between 30 degrees north and south, steady easterly winds carried sailing ships across oceans, and still steer weather today. Warm air rises near the equator, creating low pressure. Cooler air from subtropics rushes in to replace it, bending westward due to Earth's spin. These consistent winds drive ocean currents like the Atlantic's Gulf Stream. They power tropical storms and shape rainforests' climates. Westerlies, winds of temperate zones. In the mid-latitudes, winds generally blow west to east, steering storms, cyclones, and your local weather report. The westerlies sit between 30 degrees and 60 degrees latitude in both hemispheres. They're stronger in winter when temperature differences are greatest. Jet streams snake within the westerlies, steering low-pressure systems. Many airline routes use these winds to save time flying eastward. Polar winds, frozen drifters. Near the poles, icy air sinks and spreads out, drifting eastward as the polar easterlies. Polar regions have high pressure due to cold, dense air. Air flows out toward lower latitudes, curving westward due to the Coriolis effect. The meeting zone between polar easterlies and westerlies is the polar front, birthplace of powerful storms. These winds help shape Arctic and Antarctic sea ice movement. Jet streams, high-speed rivers aloft. 8 miles above our heads, narrow bands of wind race around the globe at hundreds of kilometers per hour. Jet streams form where large temperature contrasts meet. The polar jet stream is the strongest. It guides storms and weather systems. Jet streams can meander, creating ridges, warm spells, and troughs, cold snaps. Climate shifts can weaken or wobble the jet streams, changing weather patterns below. Local breezes, sea, land, and mountain flows. Even small places have winds of their own, a daily dance of air warmed and cooled by sun and land. Sea breezes. Daytime winds blow inland from the ocean as land heats up faster than water. Land breezes. At night, cooler air flows from land back toward the sea. Mountain valley breezes. warm air rises up slopes by day, cool air sinks into valleys at night. These gentle flows make local climates more comfortable. Desert winds, dust devils and sandstorms. In dry places, sun-baked ground heats the air so fiercely that spinning columns of dust dance like tiny tornadoes. Dust devils form on hot, dry days when rising air starts to spin. Larger desert winds can lift massive dust plumes that cross oceans. Saharan dust fertilizes the Amazon rainforest and even affects hurricane formation. Sandstorms can reshape dunes overnight and bury roads and fields. Famous winds, from the Mistral to the Santa Ana. Some winds are so well known they have names, bringing both beauty and danger. The Mistral, a cold, dry wind that sweeps down the Rhône Valley in France. The Fen or Chinook, warm, dry winds on the leeward side of mountains, melting snow rapidly. Santa Ana winds. Strong, dry winds in Southern California that can fuel wildfires. Sirocco, hot, dusty wind from North Africa into Southern Europe. Harnessing the wind, past, present, and future. From ancient sailing ships to modern wind turbines, humans have always turned to the wind for power. Windmills pumped water and ground grain for centuries. Tall ships relied on trade winds to explore the world. Today, wind farms generate clean electricity worldwide. Studying winds helps engineers design better cities, planes, and even sports equipment. Weather and life. Seasons of life, nature's clock. Spring buds, summer blooms, autumn harvests, winter sleep. The heartbeat of seasons guides every living thing. Many plants need a cold winter to bloom in spring. It's called vernalization. Animals time migrations, hibernations, and breeding with seasonal cues. In temperate zones, the tilt of Earth's axis creates dramatic shifts in daylight and temperature. Climate change can disrupt this clock, making some species bloom or hatch too early or too late. Rainforests. Life in the steam. In the tropics, daily rains keep the forests lush. Each drop fuels a web of life so dense it hums with energy. High humidity and steady warmth allow plants to grow year-round. Many rainforest plants have leaves designed to shed water quickly. Animals adapt to near-constant rain. Monkeys swing through dripping canopies. Insects thrive in the damp. Cloud forests, perched high in tropical mountains, drink moisture directly from mist. Deserts, survivors of scorch and chill. Where rain is rare and temperatures swing wildly, plants and animals master the art of holding on to water. Cacti store water in fleshy stems and have spines instead of leaves to reduce evaporation. Desert animals are often nocturnal to escape daytime heat. Some seeds lie dormant for years, sprouting only after rain. Camels and other animals have special ways to conserve and store moisture. Polar adaptations, living in the deep freeze. In the far north and south, life clings on with thick fur, blubber, and clever behaviors to beat the cold. Polar bears have black skin under white fur to absorb heat. Penguins huddle in massive groups to share warmth. Arctic foxes change fur color with the seasons for camouflage. Plants grow low and close together to resist freezing winds. Migrators, following the weather. Some creatures chase warmth, rain, or food across continents, riding winds and currents for survival. Birds like Arctic terns migrate thousands of miles from pole to pole. Monarch butterflies travel up to 3,000 miles to overwinter in Mexican forests. Wildebeest in Africa follows seasonal rains to fresh grazing grounds. Whales travel between warm birthing waters and cold feeding zones. Weather and agriculture, the human harvest. For millennia, farmers have watched the skies, praying for rain, fearing storms, hoping for gentle sunshine. Weather controls planting and harvest times. Droughts can ruin crops, sudden storms can flood fields. Farmers use forecasts, irrigation, and crop rotation to adapt. Climate shifts can force changes in what crops grow where. Wine regions, for example, are moving northward. Weather and disease, tiny riders on the wind. Even microbes travel with the weather, rain, wind, and heat shape how illnesses spread. Mosquitoes thrive in warm, wet climates, carrying malaria, dengue, and Zika. Warmer winters expand the range of ticks and Lyme disease. Dust storms can carry fungi or bacteria that affect humans and animals. Floods can spread waterborne diseases if sanitation breaks down. Extreme weather, life under siege. From wildfires to hurricanes, animals and plants must weather nature's worst, or perish in its wake. Forests can adapt to regular, low-intensity fires. Some seeds only sprout after flames. Coral reefs suffer when ocean temperatures spike, causing bleaching. Some species can't migrate fast enough to escape changing extremes. Conservationists help by creating wildlife corridors and protected areas. Cities, urban wildlife in weather's shadow. Even in concrete jungles, life finds a way, but heat islands and storms pose new challenges. Birds build nests on skyscrapers, adapting to new habitats. Pigeons and raccoons thrive near human food sources. Urban trees help cool neighborhoods, sheltering both people and animals. Storm drains, rooftops, and traffic create microclimates that change how animals move and live. Resilience, how life bounces back. From the tiniest moss to ancient forests, nature has an incredible ability to recover, if given the chance. After volcanic eruptions, hardy pioneer plants grow in fresh ash. Wetlands regenerate after floods, filtering water naturally. Many species adapt their behaviors or ranges to new climates. Humans can help by protecting ecosystems, restoring habitats, and respecting nature's limits. The future of weather science. Forecasting, from crude charts to AI supermodels. Once, we read the sky with our eyes. Today, supercomputers and AI see storms days before they form. Early forecasting relied on simple barometers and cloud watching. Now models run trillions of calculations, simulating the atmosphere in 3D. Artificial intelligence learns to detect subtle signals that humans miss. More accurate forecasts save lives, help farmers, and guide cities in emergencies. Satellites, eyes in the sky. High above us, a fleet of satellites constantly watches Earth's clouds, oceans, and ice. Weather satellites track storms, measure sea temperatures, and monitor droughts. They beam real-time images to scientists worldwide. New generations can even see inside hurricanes with radar and microwave sensors. Satellites are crucial for understanding climate change trends too. Drones and weather balloons, getting inside the storm. Sometimes you must fly straight into danger to understand it. Weather balloons measure temperature, humidity, and winds in the upper atmosphere. Drones can fly into tornadoes or hurricanes where it's too dangerous for planes. Data collected improves forecast models dramatically. In remote areas, drones help fill in the gaps where radar can't reach. Climate models, predicting decades ahead. It's one thing to predict tomorrow's rain, it's another to glimpse Earth's climate a century from now. Climate models combine ocean currents, greenhouse gases, solar radiation, and more. They help scientists test scenarios. What if we cut emissions? What if we don't? These models guide global climate policy and local adaptation plans. As computing power grows, so does their accuracy. Weather modification, dream or danger? Can we make rain? Stop hail? Or is meddling with the sky a risky bet? Cloud seeding uses silver iodide or salt to encourage droplets to form and fall as rain. Some regions use it to fight drought or clear fog at airports. But it's controversial, results are inconsistent, and there are ethical concerns. Large-scale geoengineering, like reflecting sunlight with aerosols, raises big questions. Extreme weather early warnings. The sooner we know, the better we can prepare. New radar and AI systems spot tornadoes and flash floods faster than ever. Early warning systems save thousands of lives during hurricanes and tsunamis. Mobile apps and social media now deliver alerts directly to your pocket. Community education helps people respond calmly and effectively. Citizen science, millions of weather watchers. Every backyard rain gauge, every phone photo of a hailstorm, adds another puzzle piece. Amateurs help by measuring rainfall, snowfall, or unusual storms. Apps let people report local conditions instantly. Citizen scientists have discovered rare weather phenomena. This massive data collection improves local forecasting accuracy, building resilient cities and farms. Tomorrow's cities and fields must bend, not break, when the weather turns wild. Urban planners design green roofs, floodable parks, and better drainage. Farmers test drought-resistant crops and smarter irrigation. Coastal communities build sea walls and restore wetlands. Everyone, from governments to homeowners, plays a role in resilience. New frontiers, weather beyond Earth. As we dream of Mars colonies, understanding alien weather becomes essential. Mars has dust storms that can cover the entire planet. Venus's atmosphere spins super fast compared to its surface. Jupiter's Great Red Spot is a gigantic hurricane that's lasted for centuries. Studying other worlds teaches us more about Earth's own weather systems. Weather and us, the story continues. The winds, the rain, the sun, they're not just something we endure. They're something we shape, and that shapes us in return. Climate change means we all have a part in deciding what tomorrow's weather feels like. Renewable energy, reforestation, and smart policy make a difference. Science alone can't do it. It takes global cooperation and everyday choices. The forecast for the future depends